Start with the baseline, a single client communicating with a single server. The user sends a request, the server computes it, and returns the response. If we scale the simulated load to 1,000 concurrent users, the server manages the traffic. The CPU works harder, but the queue clears. But when we push the load to 1 million concurrent users, the system breaks. The server bottlenecks, memory maxes out, and packets are dropped entirely. The traditional instinct to solve this bottleneck is vertical scaling. Vertical scaling means adding more compute power, more CPU cores, and larger RAM modules directly into that single machine. There is a hard physical ceiling to vertical scaling. Eventually, a single motherboard simply cannot process the required throughput, no matter how expensive the components are. The enterprise alternative is horizontal scaling. Instead of upgrading one machine, we add multiple servers to the network to distribute the incoming load. However, adding hardware is useless if the code base remains a tightly coupled monolith. A monolithic application bundles the user interface, the data access code, and the processing logic into a single executable file, making it impossible to run efficiently across multiple separate machines. We are going to build a million-user architecture from scratch to prove that enterprise hardware scaling relies entirely on strict RESTful software principles. To distribute traffic, we place a load balancer in front of 3 parallel application servers. A user logs in, and their initial request carries a session ID routing to server A. Server A stores that session data. On their next click, the load balancer routes the request to server B. Server B lacks the session memory, so the request fails, and the user logs out. For load balancing to work, the system must literally forget the user between every single request. This requires the RESTful design principle of statelessness. Statelessness dictates that each request from a client contains all the necessary information for the server to fulfill it, without relying on any saved context on the backend. The client must hold the application state. It does this by passing a JSON Web Token, or JWT, with every call. A JWT is a compact, cryptographically signed payload that securely transmits user identity and claims between parties. With strict statelessness enforced, the load balancer can send the next packet anywhere. Any node behind the load balancer can instantly serve any incoming request. Software statelessness is the engine that makes horizontal hardware scaling possible. We group our stateless application servers into their own dedicated app tier. But long-running tasks like complex report generation tie up these servers, preventing them from answering new HTTP requests. To fix this, we introduce a backend tier composed of background servers and job queues. Job queues intercept resource-intensive asynchronous operations. An asynchronous operation is a task that runs independently of the main application flow, allowing the system to move on without waiting for it to finish. If a user requests a massive data export, the app tier immediately offloads that job to the background servers and returns a success message. This physical decoupling protects the app servers. Their compute resources remain entirely dedicated to fast, continuous HTTP routing. By loosely coupling our services, we prevent localized resource limits from cascading into total system failure. Our horizontally scaled app servers funnel a massive volume of traffic into a single database. Under heavy read traffic, the database becomes the ultimate choke point. Queries begin to queue up. The solution is the master-slave replication pattern. We split the single database into one master node and several replicated slave nodes that copy the data in real time. This requires a strict routing rule. All state-changing write operations, like post, put, and delete requests, must go exclusively to the master database. Conversely, all read operations, the get requests, are distributed evenly across the replicated slave databases. Database replication is the storage layer equivalent of horizontal scaling, successfully removing the system's primary data choke point. Even with widespread replication, physically querying a hard disk is slow. We solve this by inserting an in-memory cache layer between the app servers and the database nodes. We use a caching hierarchy. Local application caches handle rapid bootstrapping, while dedicated server-side caches manage complex, repeated database queries. This connects directly to REST API principles through HTTP caching headers, specifically eTag and ifNoneMatch. An eTag is an identifier assigned by a web server to a specific version of a resource, allowing the client to check if the content has changed since it was last downloaded. When a client requests data it already has, the server checks the eTag and returns a 304 not modified header, skipping the disk query entirely. The final layer is a content delivery network, or CDN, placed between the end users and the load balancer. A CDN is a geographically distributed group of servers. It serves static assets directly from the network edge using strict cache control headers. A fully optimized caching and edge delivery system ensures the vast majority of user traffic never touches the core servers. This is the Mango app's AWS architecture diagram. It shows the transition of our abstract conceptual model into a literal production-grade enterprise schematic. On the left, our abstract load balancer maps precisely to the network and application load balancers handling the internet-facing traffic. In the center subnets, our stateless app tier and decoupled background tier map directly to the isolated EC2 autoscaling groups. On the right, the master-slave replication concept is executed by the high-availability Aurora DB multi-AZ cluster. These highly complex AWS components are simply hardware manifestations of the software design patterns we just built. Without strict adherence to RESTful constraints, specifically statelessness and uniform interfaces, this massive array of hardware would collapse under its own weight. A million-user system requires both perfect infrastructure configuration and disciplined, compliant application code. True scalability is never something you can simply purchase from a cloud provider. It is an architectural absolute that must be engineered into the codebase from day one.